Welcome to ECHO 442, Study Session 3, Linear Programming 2, Simplex Method. Introduction. In Lecture 2, we examine how to formulate a linear programming problems and how to obtain the solution using graphical method. The main limitation of the graphical method of solving linear programming problems is that it can only be applied to solve problems with two variables only. In this lecture, we will examine a method that you can use to obtain solution when there are more than two variables. Objective. At the end of this lecture, you shall be able to formulate a linear programming method in manner that solution can be derived through simplex method. A. Nature of simplex method. The simplex method provides an efficient technique which can be applied for solving linear programming problems with any number of decision variables, unlike the graphical method that can only be applied to the case of two decision variables. The simplex method makes use of simplex algorithm, which is an iterative procedure for finding, in a systematic manner, the optimal solution to a linear programming problem. The application of simplex method involves preparation of a series of tables called simplex table. For you to apply the simplex method to a LP problem, you first introduce an appropriate variable, slack, surplus, artificial, into the problem. You will start the initial solution by assigning 0 values to the primary base variables. You then start to replace one of the initial variables by another variable. You introduce the variable that contributes most to the desired optimal value and remove the variable that creates bottleneck to the optimal solution. Each time you do this, the value of the objective function improves. You continue to repeat this procedure of removing and adding variables until it is not possible to improve the objective function further. Before you apply this method, you ensure that the right-hand side RHS of each constraint has positive value. Whenever a constraint has a negative value on the RHS, you convert it to positive value by multiplying through the equation by -1. Note that this will change direction of the inequality sign. B. Steps involved in simplex method. Step 1. Convert the inequalities to equalities by adding slack variables S high to less than or equal to constraint, subtracting surplus variables S high and adding artificial variables A high to greater than or equal to constraint, adding artificial variable A high to equality constraint. You also modify the problem such that the objective function and each of the constraints will include all introduced variables with 0 coefficients where necessary. The value of artificial variable is set to -m, a very small number, in the objective function for maximization problem, and +m, a very large number, for minimization problem. Note that the values of slack variable vary between 0 and the value on the RHS, that is, 0 less than S high, greater than RHS value. Step 2. Set up the initial table and determine the basic variables. The basic variables at the initial table are those with coefficients of 1 in one row and zeros in other rows. To set up the initial table, A. List all the variables in the modified problem horizontally, row 2, column 2. B. Write the coefficients in the constraint, row 3 to row 5, column 2, and the RHS value, Bj, column 3, under their respective equations. C. Write the coefficients of each variable in the objective function, row 1, column 2, that is Ci. D. Identify the identity matrix and variables involved in it, usually the basic variables. This contains all zeros except a diagonal column of plus 1s. Write the variables under basic variables BV and write their corresponding values of the objective coefficient OC. To calculate the solution Zi, you will multiply value under column OC with corresponding value under each column. Finally, you will compute economic indicators or net evaluation row NER as triangle J equals to Ci minus Zi. Step 3. For next tables, determine the entering and outgoing variables. For maximization problem, the variable with the highest value of triangle J, key column, enters, while the variable with the minimum replacement ratio, key row, goes out. The variable in the intersection of the key row and the key column is termed the key variable. You calculate replacement ratios by dividing contribution Bi by corresponding values under variables with the highest triangle J. To calculate the new elements in the next table, you first calculate the new element of the key row by dividing each element of the key row, including Bj, by the key element to get the corresponding values in the new table. This row that you replace first is called the replacement row. To determine the new element of other rows other than the key row, use new row minus k element equals to old row minus k element minus old row minus k element in the key column, corresponding replacement row values. Step 4. Check for optimality. You do this by examining the difference between contribution Cj and solution Zj. For maximization problem, optimal solution is reached when triangle J have only zeros and negative values. That is, no possible values in Cj minus Zj row. Triangle J is less than 0. For minimization problem, optimal solution is reached when values of triangle J is either 0 or positive, is greater than 0. Step 5. If the solution is optimal, stop the iteration, else go to step 3. C. Example. Now we'll illustrate simplex method with problems with 3 variables. Maximize 8x plus 5y plus 10z. Subject to 2x plus 3y plus z less than 400. Machine has constraints. X plus z less than 150. Component constraint. 2x plus 4z less than 200. Allow constraints. Y less than 50. Sales constraints. X greater than 0. Y greater than 0. Z greater than 10. D. Solution. Step 1. Convert inequalities to equalities. To do this, you add slack variable to all constraints since they are all less than constraints. 2x plus 3y plus z plus s1 equals to 400. X plus z plus s2 equals to 150. 2x plus 4z plus s3 equals to 200. Y plus s4 equals to 50. To restate the model in a manner that is compatible with simplex method, we include the four slack variables in all equations with 0 coefficients. The new standardized modified model can be stated as follows. Maximize 8x plus 5y plus 10z plus s1 plus s2 plus s3 plus s4. Subject to 2x plus 3y plus z plus s1 plus 0s2 plus 0s3 plus 0s4 equals to 400. X plus 0y plus z plus 0s1 plus s2 plus 0s3 plus 0s4 equals to 150. 2x plus 0y plus 4z plus 0s1 plus 0s2 plus s3 plus 0s4 equals to 200. 0x plus y plus 0z plus 0s1 plus 0s2 plus 0s3 plus s4 equals to 50. Step 2. To set up the initial table, you first identify all variables, that is x, y, z, s1, s2, s3, s4. See row 2 in table 1. Write the coefficients of the four constraints under the corresponding variables. For example, the coefficients of the first constraint are 2, 3, 1, 1, 0, 0, 0. See row 3 in table 1. You also write the RHS values of each equation under column BJ. For example, the RHS value of constraint 1 is 400. See row 3. Write the coefficients of each variable in the objective function above the corresponding variables. See row 1. Write the identity variables S1, S2, S3, S4 under basic variables BV, and write their corresponding coefficients of objective function under OC. Notice that the non-basic variables are x, y, and z. To obtain the solution Zj, you will multiply value under column OC with corresponding value under each column. E.g., 0 bracket 2 plus 0 bracket 1 plus 0 bracket 2 plus 0 bracket 0 equals to 0 for variable x column. You can then calculate the values under triangle J directly. Step 3. For the incoming, the highest positive value under triangle J is 10. This identifies the key column and the incoming variables as Z. To identify the outgoing variable, you will calculate the replacement ratio as BJ/Z and select the minimum value, ignoring 0 and infinity. This shows that the outgoing variable key row is S3. Note that the key element or pivot element is 4. Step 4. To check for optimality, you need to calculate triangle J as we did in step 2. Since triangle J row has positive values, +3 and +5, the solution is not optimal and you need to repeat step 3 procedures. That is, you will identify incoming and outgoing variable and calculate new table. Another step 3. You will observe that Y is the incoming variable as indicated by the key column and henceforth is the outgoing variable. You can now calculate another replacement row. Note that the replacement element for the chosen key row is 1. With the replacement row, you can now calculate the new element of other rows using new row minus k element equals to old row minus k element minus old row minus k element in the key column, corresponding replacement row values. New step 4. To check for optimality, you need to calculate triangle J as usual. Since triangle J row has positive value +3, the solution is not optimal and you need to repeat step 3 procedures again. That is, you will identify incoming and outgoing variable and calculate new table. Another step 3. You will observe that X is the incoming variable as indicated by the key column and Z is the outgoing variable. You can now calculate another replacement row. Note that the replacement element for the chosen key row is 0.5. You can now calculate new elements of all rows and obtain final table 3 as follows. Interpretation. Produce 100 units of product X, 50 units of product, and 0 units of product Z. The maximum contribution is 8 bracket 100 plus 5 bracket 50 plus 10 bracket 0 equals to 800 plus 250 plus 0 equals to 1050 naira. Summary. The simplex method provides an efficient technique which can be applied for solving linear programming problems with any number of decision variables. You will start the initial solution by assigning 0 values to the primary stroke base variables. You then start to replace one of the initial variables by a variable that contributes most to the desired optimal value and remove the variable that creates bottleneck to the optimal solution. You continue to repeat this procedure of removing and adding variables until it is not possible to improve the objective function further. To apply the simplex method, convert the inequalities to equalities by adding slack variables Si to less than or equal to constraint. Set up the initial table and determine the basic variables. Determine the entering and outgoing variables. Check for optimality, which is reached when triangle J have only zeros and negative values. If the solution is optimal, stop the iteration, else determine the entering and outgoing variables by calculating replacement ratio and check for optimality again. End of study session 3. Thanks for listening.